On number 10, we are to find the domain algebraically and then to confirm graphically. You'll also notice in your textbook that you see gray bubbles or gray dots behind the number of each of those problems in this set, and that is an indication that these are no calculator problems. And that means no calculator in the sense that you should not use the calculator to arrive at your answer, but then when it tells you to confirm graphically on the confirmation part of the process, then you can use your calculator. So we're going to approach this from the standpoint that we are looking for those red flags that I mentioned in your study guide. And the two most typical ones, and I can't really think of one that ever comes up anywhere else, are the square root and or having an x factor in the denominator. So in this case, we have 5 in the numerator, and I do suggest that you check your numerator first. So you can make yourself a little note here that we looked at the numerator and just put NA. If you do that on your homework, it'll actually help you get a better habit going there, that you always look at the numerator first, just so that you don't overlook it. And the other thing you want to do as you approach domain is to start with the assumption that the real number set is the domain of the problem you're working on. And then you're looking for things to exclude from the infinite set, from negative infinity to infinity. And all of your domains and ranges should be listed in interval notation. Then we go to the denominator, because there was nothing going on in the numerator. And in the denominator, what you have to account for is the fact that we're not allowed to divide by 0, so that would create a non-real result. So you write the statement that you know is true to prevent that from happening, or that would make that happen. So you write x minus 3, whatever the factor is, and if this problem had 3 factors in the denominator, you would write 3 of these statements, but we only have 1. So we're going to say, well, we know that x cannot be 0. And then you solve it as if it's a normal equation, and by adding 3 to both sides, and we realize that x cannot be 3. Well, that is the only restriction in this problem, so that means that x not equal 3 is our only restriction on our domain. So we write a big capital D, and then we start with negative infinity, and we go to 3. And now, remember, when you get to the point where you're excluding a number or creating a break in your domain, you have to account for whether or not the number that you're stopping at is included. And here, it's excluded by the fact that we know it can't be 3, so you put a parenthesis. And then when your domain is in multiple pieces, you put capital U. And so then you pick back up on the other side of 3 by putting another parenthesis again, we're still excluding the 3, and then it goes to infinity, and that is our domain. So we are finished with the analytic approach to determining this domain. So now we'll confirm graphically, and notice in our graph that has 2 pieces that correspond to the 2 pieces in the domain we just found. And the one on the left would be representing negative infinity to 3. Union 3 to infinity. And the union is just formal notation to say that these 2 pieces comprise one domain, and this is the domain of this function. So the only break in the picture that we see, the red part being the picture of the graph itself, is at x equals 3, our vertical asymptote right here. And remember, anytime you create a vertical asymptote, you have a vertical asymptote that you're producing in your graph, you should make it with a dashed line. And so it is just sort of imagine it like a force field between these 2 parts of the graph, creating the shape of the graph by its presence. On number 14, we've got a little more going on, but we'll again start with the numerator. And again, we're starting from the assumption that our domain is all real numbers until our analysis tells us where there are issues and what kind of issues we have. So we start with the numerator. And in the numerator in this one, we do have a restriction. And the reason we have a restriction is that we see a square root. And the restriction on square roots is that you can only take the square root of 0 and positive numbers. So we take whatever's inside the square root, which in this case is 4 minus x squared, and set it greater than or equal to 0, because that is the requirement. So then I'm going to add x squared to both sides, and I'm going to get 4 is greater than or equal to x squared. And then from here, we could take the square root of both sides. So we take the square root of 4, and we say that has to be greater than or equal to the square root of x squared. And if we take the square root of 4, obviously we get 2, and that has to be greater than or equal to x, absolute value. Because anytime you take the square root of x, anytime you take the square root of x squared, you must keep the absolute value because x squared is positive, and you have to keep your possibilities positive. All right, well then if you write it that way, it helps you to see, based on where we had solved some absolute value equations in the earlier weeks, then the first one you write would look exactly like the one you see, minus the bars. The second one you would make the 2 negative, and you would flip the inequality and put the x on the other side. So then if you think of this on a number line type relationship, we would have closed dots at -2 and 2. And this one says we are looking for values of x that are smaller than 2, which would put us back over here. And on this one it says we're looking for values that are bigger than -2, and that gives us this range here, including the endpoints. Alright, so from that we've got that our restriction on the top is from -2 to 2 inclusive, which is why we use the brackets. And let's go back and see how we could have come to that same conclusion without all of this analysis. The analysis would be perfect here, but if it freaks you out a little bit or it intimidates you at all, just come back to this statement, because this is the core and how you could think about this. This statement says that x squared has to be smaller than 4. What kind of number can you square and keep it smaller than 4? Well, that number would have to be between 0 and 2 if you're just thinking on the positive side. And because of the square, we know the negatives would work just as well. So either way, you end up at the numerator's domain restriction, -2 to 2. So now let's look at the denominator. And the denominator should look really familiar because we just did this one on number 10. And remember, the denominator's way of restricting the domain is to have an x factor, one or more x factors in it. Well, in this particular case, we have the same one we had on number 10. So we know that x minus 3 can't be 0. It could be anything else. So again, we isolate x, and our statement is that x cannot be 3. Well, now we need to put these two bits of analysis together into one cohesive answer that represents our domain. So here's the thing. You start with the first thing that you found, which was the -2 to 2 inclusive. And so basically we have taken our set that I told you to start with earlier. We went from thinking when we walked into this problem, all right, well we've got all the numbers in the world to think about and to use or to choose from. So we went from an infinite set of numbers and narrowed it all the way down to this little finite set, and it's finite in its limits because it's bracketed on both ends, but remember that that's technically an infinite number of numbers in there as well. So now I'm narrowed down to thinking, well, this is my starting point. So then I have to bring whatever I find in the denominator into that consideration, but 3 is not in the set. If you go back to our number line perspective, 3 would not be in there. 3 would be over here somewhere. Let me switch colors and put that on the little number line there. So 3 would be like right here, so it's not even relevant. And so since it's restricted from being a possibility by the top, our final answer is -infinity, oops, sorry, wrong problem, -2 bracket to 2, and the 3 from the bottom was never a problem because we were already restricted to this as our domain. And again, we should see in the same way that on the first one we saw a two-piece domain, a two-piece graph. Here we see this tiny little, relative to the infinite space out there, this would be a tiny little picture of one piece of a graph, and here it is. And as you can see, this is the whole story for this graph, and I graphed it with the equation on screen to make sure that you didn't think I was messing with your head or something. Pay attention to the fact that this is a scale of 0.2 because this is really zoomed in. If you graph it on your own calculator, you'll see this weird little blip in the middle of your screen, and you'll have to zoom into it to see that it actually looks like this. But on this scale, 1 would be about here, 2 would be here, and then again, about -1 and about -2. So that does match right in with our domain. And it's a solid little, let me try doing that with the highlighter so you can still see the graph underneath it. You see that it's just one little stretch of a function right there in the middle of the picture that matches that domain. Number 16 is one last problem from the first set in which you're finding the domain. So same process. Now this one there's no rational function. So I've shown you a combination of two rational functions, one where the numerator did nothing. On the second one, the numerator was the whole story. The denominator did nothing. Now let's see what this one does for us. Now this one I'm going to go ahead and tell you is a trickier problem, so you might want to make a note in your packet not to get too stressed. If you were with me on 10 and 14, then 16 is just kind of to push your thinking out there just a little bit. Again, we have no denominator, or you could say we have a denominator of 1, so again the denominator is not a problem. So really all I'm doing is finding the domain of what we could think of as the numerator. So because of the square root, we have the restriction that what's there has to be greater than or equal to 0. Well, this one should be screaming at you to factor it. So let's factor out at least the x squared from both terms, and that gives us x squared minus 16. And that's greater than or equal to 0. Well, let's look at this x squared because this one creates kind of a unique problem. But I'm going to put a box around it. We'll come back to that in a minute. So let's look at x squared minus 16. So let's focus on the case where x squared minus 16, sorry about that, is greater than or equal to 0. So we add 16 to both sides first. And using the same approach we did earlier. Now this says x squared has to be greater than or equal to 16. Well, if I square 4, I get 16. If I square a number bigger than 4, I get a square that's bigger than 16. So I know that one solution to this would be that x is greater than or equal to 4. Well, then if you can think in the positive side, then you can reflect that argument to the opposite side by switching the inequality and changing the sign. Because you're either going to have one like we had on that last one where it's an interval in the middle between these two numbers, or it's on the outsides. And in this particular case, because we're looking for numbers bigger, they would be on the outsides. So this is our two limitations on our domain here now. So we can say that we know we're going to run from negative infinity to negative 4. But this one's going to be a bracket because of the fact that it's okay to take the square root of 0. So it can be 0. And then we're going to skip a space, and we haven't come back to that x squared yet. I'm going to explain that to you. And then we're going to go from 4 to infinity. Because this is two separate zeros. Now let's talk about why we have this gap in the middle. If you look at the way this square root is set up in the original equation, if I plugged in, say, 1, think about it. And in fact, let's just do that over here to the side to kind of think on paper. If we plugged in 1, we would get h of 1 equals the square root of 1 minus 16, which would give us the square root of negative 15, which is not like mathematically illegal, but we don't get a real number. So for our purposes, that's NA. Not applicable. We're going to throw that one out. Well, what makes 1 special is that when I square it, I don't get something bigger than 16 to where I can get a positive result from what's inside there. So that confirms for me that I'm not expecting anything between negative 4 and 4 to work. But you should always check 0 as well, because 0 has its own unique little properties. And if you think about it, if I do h of 0, I get 0 minus 0, which is the square root of 0, which is 0, which is legal, right? So I got h of 0 equals 0, which tells me that the point 0, 0 is a point on this function. So I'm going to go back and stick 0 in as a legal x value to have, aka part of my domain. So I'm going to stick 2 u's in there because now I have 3 pieces in my domain, and this is my answer. Now, when I go to my calculator to confirm it, and one of the purposes of these early sections in this chapter is to help you learn how to use your calculator as a tool and to recognize when it's telling you things that don't really make sense so that you're smart enough to see what it is not telling you, because there's certain things your calculator can't tell you. So let's look at the graph. Well, this confirms this piece over here would be what we discovered as negative infinity to negative 4 bracket, and we'll go ahead and put a closed dot on the graph to represent that because we confirmed that that is a value there. And then, well, we didn't actually confirm it, but we could easily confirm it because if you plug negative 4 in and raise it to the 4th power, it's the same thing as 16 times negative 4 times negative 4. So you get 0 on the inside, which is a legal value to have. So we'll get by the same argument, you would have an endpoint that's closed on the other piece of this graph. So that's our 4 to infinity. And you might be wondering, well, what about 0? Well, I can plop a point at 0 just because that works, but it's not connected because, again, if you test any point between 0 and 4, it would not work for our function. So there's the 0 we listed in the middle of our domain. And that's number 16. Now on 18, we don't have the gray bubble anymore, which allows you to use your calculator. So, but we are finding the range in this case. I will tell you that for our purposes, and it won't be long before you'll be really comfortable with this equation, but I would say probably right now you're probably not. But for our purposes, unless it's a very basic graph, you will not be asked about range without a graph to work from. So let's just go on over to the graph and look at this. So in your packet, I included the graph for you, and I'm just going to draw sort of a sketch of it here, sort of free-floating in space. But you have a picture that looks something like that. Well, if you look at your graph, you have a point at the end that we need to determine whether it's at, let me try that again. I'm going to draw it as an open circle first. We need to talk about the range in the same way that we talked about domain. We're going to start off with the assumption that it's all real numbers. And we're going to look at what happens at this point. And again, I'm going to kind of sketch it for you. This should be the y-axis. This should be the x-axis. And this should happen at 4. So obviously my scale's a little off in my sketch here, but work with me for a second. So to figure out whether that endpoint is closed or not, because your calculator will never show a dot there, much less tell you whether it's included or not. It's just the line's just gonna stop there for the graph. So you can plug 4 into your function, and the reason you want to do this is the outcome of this process right here will tell me whether I'm going to have a bracket or a parenthesis at that value. So this is equal to 5 plus 0, which is 5. So I get a value, so that means that that dot is closed. That is, the function is defined here, and the coordinates of this point are 4, 5. Well, remember, domain-X rangey, so we're going to go from our smallest y value in the picture to our biggest to describe our range. So here we go. The bottommost point in this picture is this point right here. So I start with its y-coordinate, which is 5. And, in fact, it starts with, let me erase that parenthesis. I don't know why I drew a parenthesis. I wasn't thinking. It starts with 5, but it includes 5, so I need a bracket. So it runs from 5, and then my y values from there go up. So they leave there and go up forever. So that means that I want to say my y-coordinates run from positive 5 to infinity. And there's my range. And then on number 20, my range is in a 3-piece graph. And in your packet again, you see this, and I'm again going to do a rough sketch here just so I can point at what I'm talking about. You have this parabolic piece up at the top, and then you have these two pieces down here at the bottom. Well, since we're looking at our range, and our range only, and again we're using our graph so we don't have to do a bunch of analysis to get where we're going, we'll start down here at the bottom. Okay. Well, what we know is that whatever this y-coordinate is, if I draw a horizontal line, then these two y-coordinates would have the same point. So for any pair of points I can match up all the way across, these values are all going to have matching y values. So I really only need to think about one of them at a time. So the fact that there are two sections down here that cover the same y values is sort of irrelevant to what we're doing. So now we're going to think about where they stop. Well, if you look at your graph, and mine is terribly sloppy, but if you were to draw a horizontal line across here, it would run right through here at y equals -1, because you're one step below the x-axis right here. So I know that these two pieces at the bottom that run from here up, okay, so I'm starting from -infinity and I go up and up and up, and I try to get to -1, but I never get there. Again, I'm being really sloppy in my sketch, but you can see if you look at the graph. And you'll be more confident in the statement later that you know that your graph's not going to hit that y asymptote. I'm sorry, that horizontal asymptote, y equals -1. So I know that my range begins at -infinity and runs all the way up to, but not including, -1. So I'm going to put a parenthesis there. And then I'll do union, and we'll get this other section up here at the top. Well, this other one starts up here with the bottom edge of this U right in here. So I've got to figure out where that bottoms out. Well, if you look at your graph, it bottoms out on the x-axis, the y-axis, where x is 0. So I already know it's 0 something. Well, that's really easy to figure out. So I just go up here and do h of 0. Well, if I put a 0 on the top, I'd have 3 plus 0. The bottom would give me 4 minus 0. So when I add 0 to the top and subtract 0 from the bottom, I get 3/4. Well, that's my y-coordinate at that point. So when I jump from down here just below -1 and hop up there to pick up my next y value, I start from the bottom and work my way up. So it's 3/4, and then it goes up forever, so that's to infinity. So that's the range of that one. And that's the end of this video.